Suppose you want to discover a particle. First, you need—
Wait a second, Henry. Did you just say that you're setting out in advance to discover a particle? How is that even discovering? Isn't that a little like Europeans discovering continents where millions of people already live? I mean, it's not really discovery, is it? It's more scientific fact-checking.
Exactly. Thanks for walking us through that point, John. If we're honest, we should say that the mathematical model for the Higgs was discovered in the 1960s, but the particle itself wasn't confirmed until 2012. In fact, the Higgs boson isn't even the first new particle to be uncovered at the Large Hadron Collider. The Xi-b particle, basically a heavy version of the neutron, was actually found several months earlier. You probably didn't hear much about it because the Xi-b is just a combination of quarks that we already know exist, so it's not really that exciting. I mean, if you know about cheese, and you know about crackers, then the discovery of cheese and crackers, as delightful as it may be, isn't likely to upend your universe. But the standard model of particle physics also predicts something beyond cheese and crackers. That is, about 1 out of every bajillion collisions should produce a Higgs boson, which then decays into everyday stuff like electrons and photons, which are the same crumbs we catch in the detector all the time. This battle between the tiny chance for a collision to have produced a Higgs-like particle versus all the trizillion other collisions that produce similar crumbs is part of why we need a big machine like the Large Hadron Collider at all. There were earlier accelerators that had enough energy to create Higgs bosons in principle, but they couldn't actually do enough collisions to be confident they were actually seeing a Higgs boson and not just an assortment of crumbs that looks by chance like it's from a Higgs boson. It's kind of like trying to find out if a 20-sided die is rigged. Maybe you suspect it's twice as likely to land on a 3 than on any of the other numbers, but how can you check? Well, that sounds easy enough. Just roll the die a few times, and if you see extra 3s, it's rigged, right? Not so fast. For example, if you roll the die 10 times, there's a pretty good chance that you won't get any 3s at all. That's because even though rolling a 3 is twice as likely as each other number, there are still a lot of other numbers you could roll. So random chance and big numbers can be surprisingly deceptive. Even if you roll the die 100 times and do get an excess of 3s, this is still expected to happen with a fair die once every 50 times. How much are you willing to bet that you actually have evidence for a new particle if there's a 1 in 50 chance you'd get these results by random fluctuation even if the particle doesn't exist? What if a Nobel Prize is on the line? How sure do you want to be? 1 in 1,000? 1 in 10,000? Actually, physicists are even more stringent. When we say we've discovered a particle, it's because if the particle didn't exist, there would be less than 1 in a million chance of us getting the results that we do. So if you want to convince a particle physicist that you've discovered an unfair die, you'll need to roll it over 550 times to satisfy them. And that's just to check if a 20-sided die is rigged. There are far more than 20 possible outcomes of a high-energy particle collision, so in order to be confident about announcing evidence for a new particle at the LHC, you need around 600 million collisions, every second, for 2 years. Only then can you uncork the wine to go with your cheese and crackers, and claim a successful scientific fact-checking.